nouns, they are in fact related to each other. Samples and populations are intrinsically related to one another. Why? Because samples come from populations. There's preferable kinds of samples. I want my samples hopefully to be random sets population, which is just fancy for saying everybody has an equal chance of being in my sample, because that makes my sample representative of the population, right? So putting it all together, I can't see the population, which is the ideal group I actually want to test my theory about. I can, however, see these smaller groups, the samples from the population. There are better sets of samples than others. The best ones are random sets of observations from the population. And this general process, notice it's called, it is called inference, using samples to learn about populations. So far, we're just in noun control. But how do you feel about this? Oh man, it's just like everything makes sense in terms of how I draw on the slide as I'm doing it, and then I look later on, like, wow, that's a lot of lines and boxes. Maybe you better sort of buy less of them. Does all this stuff that's happening here feel okay so far? Samples, populations, inference. Yes, no, maybe so. Cool. Got a couple of thumbs up. Excellent. Moving on then, right? This is where it starts to get a little statistics-y. Not a little, it's going to get a lot of statistics, right? The framework is going to be useful for us, right, in the theory testing environment because of statistics, right? Notice I'm going to pun, that's going to make more sense in a second. I can't help myself, right? Normally, the idea of just taking one sample doesn't actually sound like it'd be like super useful, right? Like, I know the group comes from the population, but unless I get some more information, some more statistics, it's actually going to be kind of challenging for me to use that sample to say something like systematic and scientific about the population that it comes from. Because otherwise, it would just literally, it would be like one set of information that I got one time. If I could see some stuff about it, right? But I want to be able to push my understanding beyond just the sample that I see and use it to talk about the population that I'm interested in a sophisticated kind of way, right? And that's what this little bullet point here is meant to remind us, is that science is all about the systematic, right? Not just one sample, one time, but thinking about the larger group that it comes from. And that's possible because of people in statistics. And notice, right, we're going to differentiate between these two groups pretty often. The class, and I just want to make sure this is absolutely clear, the class is not necessarily ever going to be about like the nitty gritty of the statistics that makes this possible. Instead, we're just going to like take the tools that other smart math people gave us and to use them. And instead, all I'm ever really going to want you to do is understand the ideas behind why and how we could use these tools in the way that we do, right? And this is the key one. When statisticians came up with this, what it really is going to help us do is think about, like literally, here's the key word, a thought experiment, which is a lot of what statistics is thinking about the behavior of things if we do them in certain ways. And what statisticians thought about was what happens if you imagined the world of taking lots of samples. Right, so the thing that we actually do is take one sample one time, right? Usually that's what we end up doing, is collecting data. However, statisticians enter the picture by expanding that exercise to say, well, what if you thought about this exercise as happening very many times? What would the behavior of those numbers actually end up looking like, right? And this is going to be the key thing that actually helps us move into that world of testing theories in the population, right? And I'll give you a clickbait title because I'm just like annoyed with the internet, the world of the internet. Like everything has to be clickbait at this point. There's like never a news story that just tells me what it is. It was like I was scrolling Google News this morning. It was like some person was like, well, we're going to give you a tour inside of the Bellagio. I'm like, I'm interested to see what Las Vegas looks like in this like, post-quarantine kind of world. And then like the tour was like a 30-second YouTube video. It was like, to see the actual tour, follow our Twitter page. Like, this is the dumbest thing ever. Like, just show me the thing that you said you're going to show me. Whatever, but I'm also going to make you wait. So this one weird thing about statistics, what's really shocking is it's the central limit theorem, which hopefully you've seen a lecture on, and maybe you hate because it sounds like confusing and it's hard to understand. Those things are accurate. What does the central limit theorem say? Fundamentally, this is about the statistics thought experiment of what would happen if I took an infinite number of samples, which is an odd thing to imagine, right? But what that really means is instead of just taking one sample one time, which is what we do, right? What if you imagined taking lots of samples over and over and over and over again? What would the behavior of those samples look like in what you could call repeated sampling? And this is what the central limit theorem says. If we take a lot of samples, technically like an infinite number, right? Because math, if you've ever like seen math proofs or like statistics proofs, they're all about what would happen if you did things like an infinite number of times, or like as things of remember like Mean Girls, where she's like the limit does not exist, right? They're all about things about what happened in the limit of doing things a lot of times, right? This is behavior what happens if you take lots of samples. If I imagined taking an infinite number of samples from a population, and each time I did that, I calculated something about the sample. And this is actually going to change as we evolve through the course, is what the something is, right? We're going to talk about it as taking an average today to just illustrate the point. But later on in the semester, we're going to talk about doing some other statistics. But if I calculate anything about that sample, right, and I take an infinite number of samples, what will end up happening? The central limit theorem says, if you think about what the picture, like a histogram, right, of like what all that sample information would look like, of all of them taken together, which as an aside is called a sampling distribution. I just want to make sure that this noun is connected to this right here, that this picture is called a sampling distribution, right? So it's just fancy statistics name for something that we can see. That picture actually have a shape that we know and understand, which is it would be normally distributed. Normal distributions are the bell curves that we're used to, right? These things have one hump in the center, and they're also characterized by symmetry about both sides of the normal. You know lots of things about them, right? So we talk about grades as being normally distributed. We talk about test scores as being normally distributed. All we mean is that there's a single average and there's a symmetry about that average. Cool thing is our sample information, if we take an infinite number of samples and we plot that information from the samples together like a histogram, the central limit theorem says it will look like this. Right? Statistics tells us that we know it's going to look like this. And the last part that actually makes this super cool, and I mean, if it's not clear at this point, I actually like statistics, right? And I used to I'm so bad at math, like statistics is an interesting distinction. But the cool part about this, the part that actually gets me jazzed to talk about it in the context of political science is this. The mean of this picture, right? The central part of this picture that comes from samples is going to be equal to something that's true in the population, right? Which I separate off on its own slide because it's literally just that cool. We can learn about the truth in the population by imagining taking lots of samples. And the reason that is like an interesting thing that we're taking the time to learn and talk about and use in science is because this we started 20 minutes ago shouldn't be possible, right? I never see the population, so it should be impossible for me to learn the truth about what's happening in this group that I never get to see. And as it turns out, statistics says we can learn it. We can literally learn what the truth is and what it looks like, what the population actually looks like by doing something, not by knowing everything and becoming like an omniscient social science god. And all I have to do to learn the truth is something that's possible. I can take lots of samples and I'll end up learning about it. Right? Let's look and see what that actually looks like in action. So this is the central limit theorem CLT.R script that's currently on Canvas. It's used in one of the lectures, so you've already seen it before, right? But I just want you to see where we're coming from so that if you wanted to follow along, you can, or if you wanted to do the exercise on your own later on, you can also do that, right? But we're going to imagine, right, what it would actually mean to learn about a group that we never get to see. Right, so we're going to start off with this. What does REP mean in R, just as a reminder? What does the function or the command REP mean? What if I didn't remember what didn't remember? Oh my gosh. What if I didn't remember what can I do? For any R function that I don't remember what it is.
You can REP and then do question mark, question mark.
Oh yeah, you can 100% do that. Right, so if I do that, it's going to say, it replicates the values in X. So it just repeats things, right? So what I'm going to ask for it is repeat the number 20,000 50 times, right? And this little jitter command, hey, let's go and look and see what that does. Meaning that it's going to add a small amount of noise. So it's going to move things up or down by a tiny bit. So I'm going to just look and see what this does. Right, so if I repeat 20,000 50 times, I get the number 20,000 50 times, which hopefully makes a lot of sense because that's what I asked for. However, if I wanted like a little bit of a different number each time, jitter's just going to move it up or down just a tiny bit. Right, so this is 20,000 plus like a little bit of noise in the upper direction. This is 20,000 minus a little bit of noise in the lower direction. Right, I'm going to do that for each of the following values. I'm going to repeat 30,000 70 times, 40,000 120 times, 50,000 120 times, 60,000 100 times, and so on up until I get to 150,000 360 times. Based off of the code that you see and the numbers sort of generally, what are these numbers meant to represent? What's the name of the object that they're creating together? If I look at all of this, what I'm trying to say is I'm going to pretend that I see a bunch of people's incomes, right? Here's 1,000 fake people, and I made 1,000 fake incomes for them. Some of them are super rich, right? So they're teaching or coding sports at a university. Some of them are political scientists. Some of them are graduate students, right? Which is why their income is below $20,000, right? So if I just fake a bunch of observations of people's incomes, right? I'm going to pretend like they're a population that I can't actually see, right? In other words, I'm going to make up the idea that they are representative of a group that I'm going to try and learn about, right? If I look at their histogram together, this is what I see, right? So I've got a lot of people whose average income is around $50,000. And then I've got a lot of people whose average income is about $150,000. How would I know that? Because I literally went up and looked at that right there. Right? So far, does everything seem okay? Just like what we're in here. Awesome. The question is going to be, right, if I wanted to know the true average income of this little set of people, what would I do? Literally, if we're pretending like this is the population, and I wanted to know average income of the population, what should I do? How do I pick averages in R?
The mean?
Exactly, that's it, right? So it's going to be the mean of income right here. So the true average income of this group is $88,401.25, right? Now imagine I can't actually see them, right? So if I wanted to take mean, I would have nothing to put in the middle here because I can't see the population. Central limit theorem says I can learn the same information by taking lots of samples, taking the average of each one, and then making a little histogram of all of them. And that's what we're going to do here, right? So I'm going to create some objects. The first is called people in a trial. What that means is just how many people am I sampling from the population each time. And the second is the number of trials, so the number of samples that I'm going to do. The central limit theorem says that it's supposed to be infinity. I'm going to do 20,000, and we're going to see it's going to prove the exact same point. Right? So imagine this as like you go up to this group of people, you take like a survey of 500 of them each time, and then you do that 20,000 times. And for each one of those surveys, what do? You take the average. You take the average, and you take the average. So if I run, you don't have to worry about what this line of code looks like, right? I explained it in the lecture on Canvas, but it's not important. The R side of this is not important at all. What R is good at doing is doing math, right? So that's why we're using it. I'm going to do this little chunk here, and R's already done taking my 20,000 samples, which is kind of cool, right? If I look at this object called income mean, what's inside of it is the average from every single sample that I took, all 20,000 of them, which is why I've got 20,000 average incomes, right? The central limit theorem says that if I looked at a histogram, at a picture of the sampling distribution of all of these average incomes, it would be normally distributed. Let's see if that's true or not. Oh, hey, there it is. That's the histogram of all of the sampling level means that I took. There are 20,000 of them. And if I take the picture of all of them together, it looks like this. Right? This should make sense with like what you would expect just sort of natively, right? In some of the samples, I got a lot of Mark Zuckerbergs, right? So they calculated the sample income average to be relatively high. In some of the samples, I got a lot of graduate students, so I calculated the sample average income to be relatively low. But in the average of all of the averages, right, I'm right about where the population says that I'm supposed to be. Right? Do you may remember what the true average income of the population actually is? It's $88,401.25. Where does this normal distribution looks like it's roughly centered? Where's the highest bar? Yeah, $88,401.25. I can literally figure out what the average of all the averages is by taking mean of income mean, which the object that has all of the samples in. If I do this, the average of all my samples is $88,403.56. How close is that to the true population level statistic?
That's really close.
So this is like the key part of what's happening here, right? This number, the mean of income, came from the population, right? What's the problem with that? What's the problem with statistic comes from me, like income? It's the population level data. So what's the problem with me doing mean income? If I were just like imagining being a social scientist.
The problem with me
is the problem that it doesn't factor out outliers and stuff.
Well, so I mean, like the population can have outliers in it, right? Like Mark Zuckerberg exists; he's a real person in the population, so he has an outlier level of income, right? So if I wanted to know, in other words, the true population level average income, right, I would have to include him. But what's the problem with saying, like, literally, with the idea of this as something I can do as a social scientist? If income represents the population level incomes, why can I never go to my computer and type in mean income if this represents the population?
Doesn't it have to represent like a sample?
Exactly. That's exactly right. This is impossible because I never see it. That's what we started this lecture with. I never see the population data. The only reason I could do it this time is because I made it up. Right? But on average, I'm never going to have the ability, if I want to know the average of something in the population, to type in average. I literally don't have the data. Right? So this command is impossible in the social world. This, however, and let me change colors, right? This idea, that object came from samples, right? It's me taking a sample from that larger group 20,000 times. All I did was an average of all of my sample data, right? So this is something that I can do. I can take lots of samples and I can calculate quantity about the samples if I wanted to learn. So the cool thing from the statistics side is I look at the two things that I actually learned across the two methods that I used, right? And let me pick another color. This one is impossible. I can't type average for the population. This one is possible. I can sample. I do that all the time. And how close are these numbers to each other? How close did my samples get me to learning about the population? Like the truth in the population.
It does. It like very close.
Exactly. It's basically the same. And this is going to sound ridiculous, and I apologize. It's incredible, right? It's incredible that statistics came up with a way for us to do something that is possible, to learn about something that's impossible. Not like just to get like an accurate kind of guess, but like literally to get to pretty much the truth. Right? It shouldn't be something that's allowed to happen. We can learn about something that we never get to see, but through an exercise that is like pretty easy to imagine, right? Taking lots of smaller groups from the population, learning about them, right? We do get to learn about the population level data, and that's pretty neat. Right? Questions about what this is doing or about what's happening, population samples, what's happened in the last 10 minutes. I know that somebody has a question, and I implore you, please don't just bury it in the recesses of your mind because the clock says 10:16 and maybe that's basically like 11:16, so class is already over. Because this is a few things, one of which you probably don't care about, one of which I'm sure that you do, right? A, this is not going away, right? This is fundamentally a part of what's going to happen in the next 2 weeks. And B, it's fundamentally a part of your midterm that's happening in like 3 days. So I really want you to feel comfortable with this as an idea.
Okay, so the mean income one we don't use, but we do use the mean income mean. Is that what you're saying?
That's exactly what we're saying, right? In reality, so let's just be completely sure, right? This is just an illustration. So the statistics that we do together later on in class, right? You're never going to have to be like, which one do we do again? You're only ever going to see population or sample level data, right? So you're only ever going to be able to take statistics about the sample. Right? This is just showing us that if you do what the central limit theorem says, which said that you can learn about the population by taking lots of samples, right? This is just illustrating that's not a lie. You can literally pretend like you have some population level data and take lots of samples from it. You can in fact learn about the population using samples. Does that seem okay?
Yeah.
Cool. So now it's just important for this to make sense as an exercise, right? As an illustration. When it comes time to doing actual statistics, right, for like homeworks and stuff, you're not going to have to worry about like, well, which one's the population? Because you literally, I wasn't lying, you'll never see it, right? Instead, we're just introducing the framework for how we actually end up using this. Cool. If that feels okay, then let's talk about the next little chunk, right? So let's see it in action. We just did by imagining a large group of incomes and taking the samples from them and taking an average each time. We learned about the true population, which is kind of cool. Next, we're going to transition to using some special qualities about the normal distribution to use the central limit theorem to actually do the thing that we said we wanted to do. Right? Notice, we said at the very beginning, we want to test theories. We want to test hypotheses. Right, so we don't just want to like learn about populations. We also literally want to test to see if we're right or wrong about X and Y variables in those populations. To do that, all we have to do is just pair a little bit of knowledge about the normal distribution with what we just learned. And here's what it is. Hopefully, these three notes have meaning for you because either you've watched the lectures on Canvas or you've read it about it in the book. If you've done neither of those two things, like when I say this kind of stuff, it's not like it's supposed to be a threat. It's just like this class is A, hard enough already, just because statistics and it's outside the norm of what we usually do. B, double hard because we're all electronic, which is it's A plus, and C, like it's really hard to do without a textbook, right? You can try and just do it based off of Canvas and the stuff that I say, but like the book is literally helpful in illuminating how this stuff works in a more straightforward way because it's a textbook and it's something that you can read over and over again. Right, so I just encourage you yet again to make sure that you're staying current with both the readings as well as the Canvas lectures, especially in advance of the midterm. But 68, 95, 99, what do these three numbers mean? They have to do with the normal distribution. Specifically, they have to do with not just the curve, but what's underneath the curve. So that's what this word density means. If you think about normal distribution, if you go one standard deviation, which we learned last week was a measure of spread, right? So this is the mean of the normal, which we learned last week was a measure of central tendency. So where's the average value of the normal? If you take the second part of it, which was a measure of spread, if you go one standard deviation of the normal in each direction, the density underneath this curve covers 68% of the possible values, right? So in other words, if I go one in each direction, I cover 68% of the things that are around the mean of the normal. If I go, switching colors again, 2 standard deviations in each direction, I cover 95% of the likely values. And if I go 3 standard deviations in each direction, I cover 99% of the likely values. Right? And notice, maybe you're asking, likely values of what? Remember how we're going to use the normal in this class, which is that it's going to be samples as talking about what's probably true in the population. So let's look at our picture that we came up with in R to help narrow this down a little bit, right? This is a histogram of all my information. Oh my gosh, this is magical. I can literally put it underneath the thing that I just drew. This is a picture of all of the information that we just learned from our samples as a histogram, right? So if we're talking about this as how the normal distribution can be helpful to us, this is literally saying, I think that if I had to guess what the true average income in the population is based off my sample information here, right? It's the average of this normal. It's the central tendency. It's the mean, right? Which is exactly, we just found that out by doing this right here, right? If I wanted to come up with a guess as to what I think the population is, I should guess the average of all of my averages. However, I can also quantify just how confident I am that it is or is not certain numbers by thinking about how spread out this distribution is, right? So the 68, 95, 99 rule says if I go 1 standard deviation in each direction, that's 68% of the likely values in the population, right? So I could literally say, and this is like approximating, right? I could literally say, my best guess as to what the true average income in the population is $88,400, but I'm 68% sure that it's somewhere between $87,000 and $90,000. I could go 2 standard deviations in each direction and say, because that's 95, I'm 95% sure that the true population average income is between $86,000 and $91,000. Or I could go 3 standard deviations in each direction and say, I'm 99% sure that the true population average income is between $85,000 and $93,000. Right? So in other words, the normal is going to give me 2 pieces of information. One of them is a best guess, right? It's going to give me an average that I think is equal to the true population, which is kind of cool. The second is, because of this 68, 95, 99 rule, if I literally calculate what that looks like according to my picture, I can quantify like how confident I am that the population values actually lie between some range. And that is really cool. It's going to be super useful because it's going to allow us to test hypotheses. This is like the critical part of how we're going to use the normal. Does this idea make sense? Yes, no, maybe so, looking at this picture. Just to be
Yeah.
love the little spamming of emojis that happens on top of windows. It's super useful, actually. Got a couple of thumbs up, which is great. I just like, it's beautiful if it makes sense. If it doesn't make sense to you, right, I promise you, all of you, for whatever reason, are getting this way faster than we do on average during regular semester, which is excellent, right? But if it doesn't make sense, I promise it's okay. We just need to ask questions about it, right? Before we go back to the slides, I'll just reiterate one last time why this is something that's actually useful to us, which is, somebody remind me, how did I get this histogram? The one that I just drew this picture on top of. How did I actually get that?
The samples.
What's the process? Yeah, exactly.
You
That's
took the
exactly
mean
right.
from the samples instead of taking the mean of income.
That's perfect. You're exactly right. I took lots of samples, I took their averages and drew this picture. Right? So in other words, the reason why this is fun and cool and interesting is I can make this picture by doing something that is possible. Right? And this picture tells me two things that I'm interested in. First, it tells me what I think the population is equal to. And second, it tells me what's likely to be true in the population. Right? And both of those pieces of information are incredibly useful to me as I think about trying to test theories.
Dr.
Right? So
Jordan,
this is super neat. Yeah.
I have a question. Are we going to be able to make a histogram ourselves, like on R? Or do we have to use something else to make a histogram for our next assignment?
That's a perfect question. We'll talk. So, short answer is, right, you'll never have to do this on like a homework assignment or a midterm or something, where you take the repeated sampling exercise, because it's impossible, right? You'll only ever be given, like you were for homework 1, a single set of data, like a single survey, and be asked to talk about it in a particular kind of way. And if, to the extent you're ever asked to draw this picture, you'll be asked to do it in the way that we are about to talk about. So again, we're just focusing on ideas more than we are anything else right now. So don't necessarily worry so much about like what R is going to make you do, just because you're not going to be asked to do it. And you might be asked to do something on the midterm, and I promise you right now, here and now, hands of statistics, I will tell you exactly what that is in about 10 minutes. But let's get to it first. So, normal distribution, these things are true about all normals, right? And we're going to leverage them about the ones that come from the central limit theorem to accomplish this, right? If all of this is true, that means I can quantify exactly how likely I think it is that certain values are true or not true in the population based off of results from my sample. And that's ridiculously cool, because it's not only going to give me a guess about what's true in the population, it's also going to help me quantify how sure I am that those two things, that population looks like I think it looks like. How does that happen? To get more directly to your question, statisticians, notice, right? So don't worry about where formulas come from. We're just going to use them because statistician gave them to us. Took the sort of central limit theorem infinite sampling exercise and then thought about, well, then how do we use that in the world that we actually operate in, which is having one sample, right? In other words, because of the work that we're about to look at, we don't have to imagine taking an infinite number of samples every single time. Instead, we're just going to use formulas to apply this framework to the world in which we only have a single sample's worth of data, right? So that's the world we're going to be in all of the time, is having a single sample, right, and using formulas to imagine what that picture looks like. And that's what I'm going to ask you to do on the midterm. We'll go through an example together. There's also lots of examples on Canvas. Finally, just before we look at these things, as a reminder, and we're going to keep this the entire way through the rest of the semester, talking about this difference between samples and population, right? In other words, it would be kind of convenient if we had like a notation way of separating this part of R, the side that came from the population and the side that comes from samples. The way that we separate them is through this symbol. The population, or the sample one, gets this little hat. So when we're talking about quantities that we estimate from samples, we're going to give it this little hat symbol to denote it away from the population that we assume that we're talking about. So what do statisticians tell us? First, we can draw this histogram, which is really cool. What does the central tendency look like? It looks like what you think. Just imagine, right? If I take a sample and I calculate anything about the sample, right? My best guess as to what the population looks like is what my sample looks like, because anything else would be irrational. And during the lecture notes that are pre-recorded on Canvas, I give you this example. Suppose, like we did last week, I take the height of everybody in Poli 3000, right? I get all of your heights together in inches, and I calculate the average, and I estimate your average to be about 66 inches or something, right? So that's the average height of the 12 people who are in class today. Then I ask you, how tall do you think the average student is at Auburn University? What should you say?
That is an impossible question to answer.
Well, so it is an impossible question to answer, right? Like the population, because it's like population, right? Am I ever going to do a survey of all Auburn undergraduates that have ever gone to Auburn and ask them all their heights? The population.
So, first off, it's not specific. Second off, that's too many people.
Yeah, exactly. It's both those two things, right? So I'm never going to see that group ever, right? Instead, what I might be able to do is take a smaller group, like a sample of you all, and calculate your average heights and use this to say something about what I think is probably true about the population that I never get to see, right? So we're going to carry that logic, right? If I did this, I took you as a sample, I calculated your average height, and then I said, using this information, how tall do you think the average undergrad is at Auburn? What should you guess?
66 inches.
Why should you guess 66 inches?
Because we got a sample of the Auburn population.
That's it.
So you'd expect it to be, right there.
That's exactly right. Right? If I got my sample information, right? If I have information from the sample, the only logical thing for me to guess about the population is what my sample said. Right? Moving over, like imagine this world back in R, right? Where I have an average of all my averages. And so it's like using all this information, how much money do you think the average person in the population makes? You're like $90,000. That's irrational, because all of the sample information led you to say something in particular. So we're going to use our samples to inform a best guess about the population. Right? So the sample best guess is always going to be what the sample says. Does that make sense? Yes, no, maybe so. Cool. So we're going to start from where the sample says. Right? So the sample suggests that people are 66 inches tall. Then that's what this bullet point says. Right? So we're going to assume that the histogram, the normal distribution that we get to draw according to the central limit theorem, is centered, right? The mean of it is on the sample value, because anything else would literally be irrational. It wouldn't make sense for me to guess that the population looks different from what my sample looks like, assuming that my sample is random and representative, which is why we need random representative samples, right? In statistics notation, if you want to practice using this little hat magic, that can be expressed as saying, I think the population height, the true average of everybody, is going to be equal to the average I calculate for my sample, right? So I'm going to guess that my hat is equal to the population, right? Because again, anything else would be irrational. However, I want to respect the fact that I could be wrong. Like, what if I don't know, like word got out that this was super cool, and so the entire Auburn men's basketball team took like my class over the summer. Would that sample estimate be a good estimate of the population true average height? Why not?
Because that's well,
Yeah, they're not random, right? They are not random, and they're not random in a very particular way, which is they tend to be tall. Is the That's the thing that kept me from playing basketball competitively, not the fact that I have like a 4-inch vertical. Right? If I have that, I want to respect the fact that this, right, my sample is my best guess, but I could potentially be wrong. Right? And I want to quantify what I think is likely true in the population. That's where the spread comes in, which is the next bullet point, right? Statistics is just going to give us formulas for what that spread is calculated as. The example that you're given for the current set of modules is something called the standard error of the mean. It's called that because anytime we're talking about uncertainty around a sample statistic reflecting a population, that uncertainty is called standard errors. Right? This is going to come back about a cajillion times at this idea of a standard error. So that's why it's bolded. And I just want you to feel like if there's like a few key nouns to walk away from today with, so far it's samples, populations, inference, and standard errors, right? So this is a measure of the spread of what we think the population might look like around our sample characteristic. The standard errors are going to be different based off of what we're calculating about the sample. So far, and for the midterm, the only thing we've calculated is an average, right? We've only calculated averages so far. So that's why we're going to talk about something called the standard error of the mean. And we're actually going to do that in R together to illustrate the point, right? So let's look at a central limit theorem applied example, right? So imagine I've got a poll of 1,000 people. N always represents the number of people that I have, right? And I use numbers 0 and 1 to represent people who do not approve and who do approve of something, right? So people is going to be my sample of people, right? If I look at people, I've got 1,000 of them. I've got 530 zeros, and I've got 470 ones. So out of my 1,000 people, how many of them approved of whatever the fake thing is that I'm evaluating here? What number of people said that they were a 1 on this approver group?
470.
Perfect. 470 said, I like it. 530 said, I didn't like it. If I wanted to calculate the average approval, I can just do average of the sample, and I'm going to get 0.47. So 47%, because a percent is just the proportion, 0 to 1, times 100. So 0.47, 47% of people, if they approve of whatever this is. Also notice, right, I don't know why I'm playing around with this. You can verify that R calculates averages. It's the sum divided by the number of people that I have, and look at that, it's 47%, right? If I wanted to start to think about the spread, though, right, the spread around it, I'm going to need a measure of the dispersion, right, around the normal distribution. And if you remember from the slides that are already on Canvas, the formula for, and let me just write it out, standard error of mean is equal to, and you don't have to have these memorized on the midterm. It's A, it's open, no, right? But B, you'll also be literally given a formula sheet that has all the formulas written down right there next to it. All you have to do is just know how to use them, and that's it, right? So the formula for the standard error of the mean is the standard deviation of whatever the variable is divided by the square root of the number of people that I have. What does that mean in terms of how we use it? If I wanted to get back all the way to your point, to draw a histogram here, right, about if this is just a sample of 1,000 people, and I wanted to do this little, I've actually been doing like a really good job of drawing normal distribution so far today, which is like challenging after like the 100th one, right? So if I wanted to do this little exercise where I drew my normal distribution to try and learn about the population, right? What should I assume the population average approval rate is? if this is a sample, right? If I'm pretending that this sample came from a population, right? What should I assume that the population average approval rate is if my sample approval rate is 47%?
47%.
Why should I assume that? Just
The sample from the main population is expected to be, excuse me, constant.
perfect, right? Remember, we assume our samples are equal to populations because they're random groups drawn from the population. So I should assume that this population approval rate is 47%. If I wanted to use the 689,599 rule to see what's likely, what's unlikely, I just need to know how far to go out in each direction. That is where this formula for the standard error comes in, right? I'm talking about means and average approval rate. So I'm going to use the formula for the standard error of the mean. And you don't have to know where this formula comes from, right? It just comes from statistics. I don't care like why it's this formula. Right? Because all I ever do is just take tools that other people who are smarter than me use and apply them to things I'm interested in. Right? So the formula for the standard error of the mean is the standard deviation divided by the square root of the number. Right? If I wanted to know what that is, I would just make it for me. The standard deviation of my sample, the object of the sample is people, divided by the square root of the number of people that I have, which is n. I run this line and I look at this object, R is going to tell me that the standard error of my polling example, the standard error of the mean of it is 0.0157908, right? So if I wanted to take this and apply it to the picture that I've been drawing, that means that I would go plus 0.015, and then if I wanted to go another one, plus 0.015, and then minus 0.015, minus 0.015. So if I go, hold on, sorry. If I go I'm not angry at all. If I go one standard error of the mean in each direction, that means I'm 68% sure that the population level approval rate is between this number and this number, 0.47 plus and minus 0.015, which is the standard error of the mean. If I go 2 in each direction, then it's plus or minus 2 times 0.015. Right? Just as a offhanded, what is 0.015 times 2? 57908 times 2 is 0.03. You ever see a poll reported by USA Today or whoever and says that the margin of error is plus or minus 3%? Ever seen that before in a newspaper? This is literally where that comes from. All they're reporting the formula for the standard error of the mean and saying, right, we've got a guess as to what we think the true population level approval whatever is, right? And we're 95% sure if we go 2 standard errors in the mean in each direction that it's between some values, plus or minus the margin of error. It's literally, they're using the central limit theorem to quantify how sure they are. And now you know where that comes from, the logic behind it. Right? So I'm just going to use R as a calculator. I'm going to say the average, let me get rid of this really quick. The average approval rating is 47% just by calculating the mean of the sample. Then, if I combine, and let's just move this across so we can see it all together. If I combine the mean minus 1 standard error, the mean and the mean plus 1 standard error, this range is what I'm not 68% sure the population looks like. I'm 68% sure the true population approval is between 45% and 48.5%. If I combine the standard error in 2 of them in each direction, I'm 95% sure that the true population value is between 43.8% and 50%. And finally, if I combine 3 in each direction, then I'm 99% sure that it's between 42 and 52%. Does this seem okay? Like what this is doing, how this is drawing a picture? right? If I wanted to just plot all of these things together, then I can force R to do that. Right? Here is literally a picture of that normal distribution, right? So this is the key differentiator is this isn't built off of like the other histogram was taking lots and lots and lots and lots and lots of samples and plotting the histogram of all of the averages. This is just pure statistics, taking the mean of the sample and using a formula to calculate what that uncertainty, what that spread actually looks like. Right? The reason why I might like this is this actually reflects what I literally do. Right? I take one sample one time. I don't take lots and lots and lots of them. I take one sample and I can learn the same kind of picture just by taking a single slice of data. And that is pretty interesting and super useful. This where this idea comes from. Seem okay? Does it feel like it makes sense? Questions? Are there questions? I understand we've been at it for like an hour, but it's just, I promise, this is today and a little bit of tomorrow are the two hardest lectures we're ever going to have. I promise. So if you have any questions about anything, please fire away. If not, sure.
I have one question, but it was about like an example that you did in one of your lectures, like on in the modules. But it was kind of similar to this one, but it was the one where you did like 1,000 person sample for like a candidate, and it was like, is there a chance that it's like a 50%? Do you know which one?
100%.
Okay. I saw that you did 68%, and then you did 95%, and then you like said it was between those two numbers. I'm confused on why you didn't go to 99%.
I could 100% go between them. Right, so
Okay.
it's a great question, Amanda. Here, let's just illustrate the difference, right? So if I do this, right? So I'm just going to rerun these 3 lines of code. Actually, what I'm going to do is get rid of all this stuff and then rerun these 3 lines of code. Right, so you're absolutely accurately saying is that this represents the values that I'm 68% sure that the population level approval based off of my sample data is somewhere between 45% and 48.5%. I'm 95% sure that it's between these two numbers, right? And then I'm 99% sure that it's between these two numbers. Which of them should, like, how sure should I be? 68, 95, or 99?
99.
Here's the secret answer. It's just up to me. It would probably be better. Like, I want to be as confident as I possibly can, right? But it's actually going to depend a little bit on the kind of science that I'm doing, right? Drug trials, they don't stop at 99. They actually go out to like, I want to be 0.000000000, like 99.99999. That sure that my drug doesn't have adverse side effects, right? We stop here because we're social science, and it actually doesn't really like matter that much if we're wrong. If like, oh man, peace doesn't actually cause democracies or whatever it is, right? So we stop at being 95% sure just out of convenience. But you're absolutely right. So we'll get into the nitty gritty of how we use it and the way that you suggested in a second. But that's a great question. The answer is just I can choose how confident I want to be. And there's like no reason to pick 95 versus 99. You just have to state which one you want to be, right? Do you want to be 95% sure, or do you want to be 99% sure? Does that seem okay?
So just because like the answers are so like close together, like when you did like 95 and 99, it's just that's why it really doesn't make a difference.
That's exactly right.
Okay.
It's up to me to be how sure I want to be. But it'll make more sense to answer the question in like 7 or 8 minutes when we circle back to this, like testing an actual hypothesis instead of just as an exercise. So let's do one thing really quick, right? Which is, so I've got that one picture that I just drew, right? We're going to actually show that it's equivalent to the other exercises that we did, right? So imagine I created a population. Here's my object called people. It's my 530 disapprovers and 470 approvers. What if I just combine a lot of them, right? So I create a fake population by just combining lots and lots and lots of people. So if I look at the mean of the population, right, by assuming my sample is representative, right, the mean of the population is going to be equal to 47%. I'm going to do the same thing as I did up in the income example, which is take 10,000 polls of 1,000 people each and calculate the average of each of those polls. And if I do that, right, and I look at, again, just a histogram of what that looks like, it looks like this. What does the average of the histogram of my 10,000 poll means look like, approximately? Where does it look like this picture is centered?
Well, before it looked like a.
Yeah, about 0.47. All of you are correct, right? The cool thing is if I took a standard deviation of all of this, right? So what's the measure of the spread of this normal? What does this look like about? 0.015. Where have I seen that before? What is the standard error of the mean that I calculated using my one sample, the standard deviation divided by the square root of n?
It was 0.15.
Yeah, so these also look identical. In other words, right, statistics is not lying to us. If I did the infinite samples way, right, this is talking about, like, the central limit theorem says take lots of samples, form the histogram. This is that histogram, right? And it's saying the average of it is going to look the same as taking one sample, and the spread of it is also going to look the same. Right? So statistics is showing us two identical pictures. Finally, let's look at those two plots next to each other. This is, right, on the top is the picture of the histogram that we can draw based off of one sample. On the bottom is the histogram of the 10,000 polls and their averages drawn together. How would you describe these two pictures as being related to each other? Do they look similar? Do they look different in terms of where they're centered? My dog's going crazy. I don't really know what's happening right now. Do they look similar? Do they look different?
They're similar. They're frequency Poli X.
Are they centered at about the same place?
Oh, yes, they are.
Do they have, like, roughly the same amount of spread, would you say?
Yes.
I mean, like, that's kind of cool, right? It's literally, statistics is showing us that if I do one sample and use formulas, I get the same picture as thousands of samples and using a picture, right? And this is the key secret sauce of why statistics is useful, is because I want to live in this world. I want to live in the top world of using formulas and taking one sample because it's cheap and less expensive than taking lots of samples over and over again, right? And statistics says I can talk about it as if I'm in this world, and both of them, right? And here's the key part: both of them give me information about the population by only taking a single sample, right? Which again, shouldn't necessarily be possible, but it's something that I get to do using sample level data, which is actually kind of neat, right? So moving back to the slides for right now, we'll see how those two things are equivalent in R. That's what we just did, right? That the picture on the top is the same as the picture on the bottom. The only difference is one came from one sample, the other came from thousands of samples. I love that as a scientist who is cheap, because it means I can do one sample once and learn about it as if I did it many times. So to get a little more directly to Amanda's point, right, how is this actually useful for us in terms of testing our theory, circling all the way back around to the first slide, right? We're going to do it, and then I'll go ahead and underline the keywords here, right? So we're up to sample population inference, standard error, and then finally null hypothesis is the next set of nouns that we're going to add to our vocabulary. We're going to take all this information to test the null hypothesis, right? And it's going to be our friend for the entire semester. The null hypothesis asks the question, what should I observe if X and Y are unrelated to each other? In other words, this is a hypothesis that I want to reject if my theory is right. Right? So I can literally, if I hypothesize that X and Y are unrelated, and I find out that I don't think they're unrelated, that means I get to conclude that they are related, right? And let's figure out why this is something that's true. We're using one last time our height example. Actually, let's use the campaign polling example that we just did, right? So the mean was 0.47, right? And then I'm just going to go and cheat and take the values. One standard deviation, or one standard error of the mean, in each direction was, so 68% sure was from 0.45 to 0.485, 0.485, two standard errors, I'll switch colors, was 0.438 to 0.501, and three standard errors was 0.422 to 0.517. And to be absolutely sure, this is the kind of picture that you're going to see on the midterm, is one that has these values that represent 68, 95, and 99% of what I think is likely in the population based off of the sample. All I did was start from the mean and go out one standard error in each direction, two standard errors in each direction, and three standard errors in each direction. Question: what do I think is the likely approval rating in the population? What's my best guess to be absolutely sure?
Your best guess is going to be your center, your 0.47.
Exactly. Perfect. Absolutely right. My best guess is equal to my sample. Right, so I think that in the population, the true approval rating is 47%. Question: how confident are you that it's 47%? How sure are you?
I'm 68, 95, and 99.
No, you're right. So follow that same logic. What's the percentage you can say about what your 68% about?
I'm sorry, I can't see the little the amount.
Here, let me just. So if you want to use these numbers instead.
Cool.
Just cheating, and this is where I got them from. Is in R.
Cool. I'm 68% from 0.45 to 0.48. I'm 95 from 0.43 to 0.50, and I'm 99 from 0.42 to 0.51.
You're absolutely right. So you're 68, 95, and 99% sure that those ranges are where the population value is, right? Thinking about that, did any of those sentences help you say how confident you were that it's equal to 47%? In other words, do any of those sentences help you to rule in that value?
Yes.
How so?
Because it's in the range of. Well, actually.
Yeah, so I'm 68. You're right. I'm 68% sure between those two values, right? But does that mean that I can have any confidence over it is equal to 47?
No.
So you're totally right. It's so important to understand it, and it's so backwards, it's unreal. But statistics is built around this logic of I actually, starting from the center, I can't express a confidence about how sure I am that number is right, because it's the number that's talking about the population, right, that I never get to see. However, I can express how sure I am that the population is between some range. And so I'm 68% sure that the population is between 45% and 48.5% sure. And I'm 95% sure that it's between 43.8 and 50.1. And so now I can start to rule out numbers that are outside of that range instead of ruling in numbers that are inside of it. Right. So to answer your question, Amanda, right, if I wanted to sit, imagine I took this poll, right, and your candidate asks you, it's well, how can you be 95% sure that like you didn't just get a crappy poll, right? And that my approval rating isn't actually 55%, right? You can literally test that using this framework by saying, well, I'm 95% sure that the population values are from between 43 and 50, right? And that does not include the number that you just asked me for, right? So I can rule that out as a possibility. That's what statistics are really going to allow us to do, is instead of ruling in numbers with confidence, they're going to allow us to rule out numbers with confidence, which is why we use this thing called the null hypothesis, right? If I can't rule in the thing I'm interested in, then I can try to rule out the thing I'm uninterested in. And to think kind of bizarrely about it, if I think X and Y are related, then the thing I want to rule out is the possibility that they are unrelated to each other. Does that seem okay? The really odd idea, but that's what the null hypothesis is ruling out the idea that two things are unrelated. Because if we can do that, then we would think that they are related to each other, which is what we actually want to conclude. In other words, statistics is built backwards because it has to be, right? I'm going to get an estimate of how related I think X and Y are, right? And I have to talk about, well, given that estimate, how sure am I that they're not actually unrelated in the population, the group that I never get to see? Seem okay? Yes, no, maybe so. Cool. It's a really odd idea, so let's talk about it a little bit more. Right? Here's how that looks like. Literally, this is just words to describe the actual picture that we just drew. And we can actually, let's just look at another picture of it. This is the 689599 all lab is on Canvas, right? Just verbatim, so you can run this whenever you feel like it. Right? I'm going to start with like another sample of exactly the same people and exactly the same way. Who are zeros and ones, right? If I want to know how many people are in the sample, just by cheating, I can do length of the sample. So R is going to tell me there are 94 people. The mean of the sample is 28.7% approval of whatever this underlying thing is. 689599, just putting it together, and the central limit theorem say I can be 68% sure that the true population level mean is between the range is established by one standard error below and above the sample mean. I can be 95% sure it's between two standard errors below and above the sample mean, and three standard errors that it's below and above the sample mean. So all I have to do is just calculate what those things look like. I'm going to break this formula into two different parts, right? So the standard deviation is the numerator of the standard error of the mean formula. So let's just write that down again. Where the standard error of the mean is the standard deviation divided by the number of whatever it is that I have. Right? So I'm going to break that formula here. The standard deviation, or the standard error of the mean, is literally 0.0469. And so that's how far I want to go in each direction to draw a little picture. Let's actually sit here and make an object that does that. And now I'm going to draw a little plot. Right? So if I run all these things together, R is going to draw a picture for me that literally says, this is the range of values that I am 68% sure about, that I'm 95% sure about, and that I am 99% sure about. All it is just take the sample average and go 1, 2, and 3 standard deviation or standard errors of the mean in each direction. So if somebody came up to you, seeing this data and said, can you be 95% sure that the true population approval rate isn't actually 15%? What would you say to them? What are you 95% sure the population looks like here, given this sample?
I'm 92% that it's 0.2, and I'm 90% that it's between 0.2 and 0.04. I mean 0.4.
Right. So you're absolutely right. So we would just like want to make sure that we're using the specific number, 68, 95, 99. So I'm 95% sure it's between whatever that is, which is right under 0.2, and whatever that is, which seems like it's about 0.38. Right? I could calculate what they are just by. Ooh, that's the wrong one. I like close this actually. by just doing this, right? So if I did that, then I would be between 0.19 and 0.38. Does that include the number that I was interested in, 0.15? In other words, thinking about this, like literally, this is called a confidence interval, right? Which we'll see on a slide in just a second. I'm 95% sure that the population is between these, oh geez, two red bars. Right, so I'm 95% sure that the population level mean is between these two numbers, which means I'm 5% sure that it's not out here, right? So can I be 95% sure that the true population mean isn't 0.15?
I'm guessing yes.
How so? You guessed correctly. You have it absolutely right.
If you're
Just
90%,
explain your logic.
if you're 95% sure it's between all these numbers and 5% sure it's not those numbers, and then you added a 1 point something, which isn't even on the graph, it just doesn't make sense. I don't know how to explain it.
No, you're right. Right. So just take your sentence to its logical conclusion. You're absolutely right. I'm 95% sure that it's between these two numbers, which means I'm 5% sure it's everywhere else. Right. So somebody said, well, can you be 95% sure that it's not this? Well, that's outside of my 95%. So 100% I can. That's a terrible thing to say. I'm sorry. I can be 95% sure it's not this because I am 95% sure it's somewhere between here and here. And what you just asked me about is outside of that 95%. To Amanda's question, can I be 99% sure it's not this number? Why or why not? What numbers am I 99% sure about? I would just go out one more in each direction.
I guess so. I mean, it's close to there, but it's not there.
Boom. And that's all I would have to say. It's just yes or no, right? It's outside of it, so I am 99% sure it's not equal to this, right? I could run this again, just making R do the math for me, right? So I'm 99% sure that the population is between 0.146 and 0.427, right? And then I would just see if that includes or doesn't include whatever number it is that I'm interested in. Does this idea of using this to test hypotheses make sense? Does it feel okay? What questions do we have about how this works and what this is and what it's doing?
So, for example, on the midterm, when you ask these questions, do you have to do it paragraph form, or can you just be one sentence straightforward?
One sentence straightforward. The beautiful thing about statistics is you never have to tell me a story. And statistics has right answers. And as we'll see through the semester, those answers are literally memorizable, which is kind of fun, right? All you have to do is just know the logic and then say, how do I go to this range and look for certain values that I am or am not interested in? And that's it. Right? So the midterm, thinking about what's going to look like because it's going to be online, right? The midterm will almost certainly give you something. Oh, stupid. Ignore what I'm doing in R. Ignore everything that's happening right now. Pay no attention to the things that are happening here. Right? The midterm would give you a picture that looks like this, right? And say, what are you 68% sure about? What are you 95% sure about? What are you 99% sure about? And then just ask you if it's inside or outside of this range. And everything that you're worried about will be taken better care of, right? Where the axis will have more precise numbers on it so that you can be more precise if you want. I would never ask you, what I'm trying to say is, right, I would never give you this plot and be like, can you be 99% sure it's not 0.14, right? Which seems like it's right here. I'm not a trick question person. I am a partial credit person to the bajillionth degree. If anybody's ever taken a class with me, hopefully that's come across before, where the challenge isn't to try and dock you for specific nonsense. It's just to make sure that you are answering the question in its entirety. This idea seem okay, how confidence intervals allow us to test hypotheses?
Yes.
Awesome. We're going to do, I think, one more slide on it today. Actually, yeah, and this is it. So the last thing we're going to do today is pair this with something called p-values, right? And this is the whatever number that we're on. I think like sixth noun that it is that we're going to learn, right? What is a p-value? There's a bunch of words. Don't focus on the words yet. Focus on this. The confidence intervals said, right, I'm going to go here and tell you, someday maybe I'll get good at drawing right on top of these lines. I'm 95% sure that the population lies between these two numbers. P-values say, I'm 5% sure it's somewhere else. Right? So confidence intervals talk about the middle in. P-values talk about the sides out. So when it says here, right, that we're going to use a p-value of 0.05, where that comes from is if there's 95% in the middle, that means there's 5% left over in each of the two tails. So the p-value is going to quantify, is it out here in the things that I think are unlikely, yes or no, right? So it's going to be really convenient for us because it's going to distill everything about confidence intervals down to a single number, which is just how far out in these unlikely values, or you might think of them as being the tails of the picture, how far out in the tails is the number that you're asking me about? And based off of that, do I think that number is likely or unlikely? Does that seem okay just as an idea? Cool. So we're going to leave that for today and pick up here tomorrow, right? So we're going to clarify tomorrow some more on confidence intervals and p-values and how they're related, right? Just be sure to do that. Like, make sure that you're keeping up with the lectures, and also to have watched the bivariate hypothesis testing lecture tomorrow so that we can talk about those things and clarify any questions together. I'll have more information on the midterm tomorrow too, because I understand that's probably information that you want, especially as it pertains to this, like what you need to know, what you don't need to know. I just have to make the midterm first. And it's going to look a little bit different because it's all online, so I have to think about some stuff, but don't worry about that. We'll talk about the midterm in a lot of detail tomorrow, so don't worry about it. Questions on this today, on this idea, on this approach, on what it's doing, on what inference is, on any of it? Cool. So I appreciate everybody being patient through this as just a slog of information. I reiterate my promise that I made at the top of lecture today, which is this is the most challenging lecture we're ever going to do. It's also probably the most boring one we're ever going to do, where I just end up talking for the longest. It's not always going to be like this. And just encouraging you to stick with it, because it's unfortunate, right? This will, just like art, this will get better as an idea. The challenge is it's not going away as an idea, right? So if it feels uncomfortable, if the idea, especially if inference feels uncomfortable, or looking at this picture, thinking about likely and unlikely values feels uncomfortable, like ask me today or tomorrow during office hours, or right now if you feel like it, because it's just super important for us to get on the same page, especially before the midterm happens. But any questions or anything? Cool. Just a reminder, office hours start in about 15 minutes. Just let me know if you plan on coming by, but if not, I'll see you all tomorrow.
All right, goodbye.
Thank you. Bye.
Yeah.
Thank you.